There are many applications of integrals. One of them is for finding the average value. Now, to find a formula for the average value, if you have a function that's integrable, have a starting point and an ending point for that function. I like to think about this as an ant farm. So you can buy an ant farm, which is basically two pieces of glass or plexiglass very close together, and then you fill it with sand, and then you send in a little card and you order some ants to put into your ant farm, and you turn them loose in there, and then they dig little tunnels that you can watch. But let's imagine before the ants come in the mail, you have your ant farm and you have created the top of the sand to match the graph of a particular function f, and you want to know what's the average value of f. Well, it stands to reason that the average value should be the value that the sand would shake down to if you were to take your ant farm and level the sand. So this should be the average value for the function. Now, if you level out that sand, the amount of sand that was in the ant farm before is the same as the amount of sand after. Now, the width of between the two pieces of glass or plexiglass has stayed the same, so that would mean the volume has stayed the same and the width has stayed the same, therefore the surface area would stay the same. Now, we can find the area in two ways. If we use the average value, the area will be since that's a rectangle, the area will be the average value of f times the length of the interval, which is b minus a. On the other hand, we could find the area underneath this curve by slicing it up really finely and taking f of x times the width of each slice and summing those all up from the first to the last. And this actually gives us an equation that we can solve to find the average value of a function of f. It would be 1 over b minus a times the integral from a to b of f of x dx. So that's how we find the average value. You can remember it from the ant farm example. Just imagine having the function sort of made in the sand and then shaking it to level out the sand to find the average value. The two areas, the area before shaking and the area after the shaking, should be the same, and so you can solve for the average value of the function. Here's a little example. We've got this function and we want to find its average value on a particular interval. So let's see, our formula for the average value would be this. The average value of f would be 1 over the interval length. Let's see, our function goes from -3 to 3, so that would be 1 over 3 minus 3 times the integral from -3 to 3 of the square root of 9 minus x squared dx. Or since subtracting -3 is the same as adding 3, we have 1 over 3 plus 3, which is 1 over 6, times the integral from -3 to 3 of the square root of 9 minus x squared dx. Now, to actually find that integral, you could think, well, I have to do a limit of Riemann sums. But not necessarily. If we can see what this shape is, we have our function here. If that's our y, if the output's the y value, then we have the function y equals the square root of 9 minus x squared. So y squared is 9 minus x squared when I square both sides. So x squared plus y squared is 9. Now I recognize that that's a circle of radius 3, right? And centered at the origin. So, and we only have the place where the y values are positive, so we just have the upper part of that semicircle. So I'm going to draw 3 to the left and 3 to the right, and what we have basically is this semicircle. So to find the integral from -3 to 3 of that function, we know what we would be doing is taking a tiny bit, this super tiny small slice that's dx wide, and it's f of x tall, f of x here being the square root of 9 minus x squared. So this is calculating the area of one slice, and we are smoothly summing up all of those slices to get the total area. Well, I know how to get the total area another way, because I know that the area of a circle is pi r squared. So if we had the whole circle, the area would be, since the radius is 3, the area would be 3 squared times pi, or 9 pi. But since we only have a semicircle, then the area will add up to be 9 pi over 2, right? Half the area of a full circle. Now I know what the average value will be then. Since we know the average value of that function is 1 over the interval length times the integral, and we just figured out that the integral was 9 pi over 2. If we multiply, we have 9 pi over 12, and we can reduce, because 3 will go in the top and the bottom, we get 3 pi over 4. Okay, so that tells us that the average value of this function, although it spends some time down near 0 and some time up near 3, the average value is 3 pi over 4. Since pi is just a little more than 3, this is a little bit more than 9/4, or 2 1/4. So 3 would be all the way to the top of the circle. The average value is around 2 1/4 here. So that's the average value of that particular function. Now, you might ask, we have this formula for average value. You might ask, how is that related to what we usually think of as the average? Well, suppose we were averaging test scores, and someone gave us our scores in a table like this. They said, okay, there were 5 people that got a 96, and there were 2 people that got a 91, and there were 3 people that got an 85. I don't want to get too many scores here, so maybe I'll stop and say there's 4 people that had a 75 here. Then the way you could calculate the average from this data would be to take each score, 96, times its weight, right? After all, I would need to add up all the scores for all the individuals and then divide by the total number of individuals. So since 96 has a weight of 5, or there were 5 people that had that score, I would take 96 times its weight, and 91 times its weight, and 85 times its weight, and 75 times its weight. Then I'd have to divide by the total number of scores, which would just be the total number of people, which would just be the total of all the weights. And that's how I would calculate the average of those numbers. When we're calculating the average value of a function, we're doing something very similar. We have here, starting at some point A and ending at some point B, a function, and what we do is we break it up and we break up this interval into tiny little slices, and over that interval we say, okay, this amount, we have delta x here, this amount had a score that was this high, f of x, and this amount, this other delta x, maybe this is delta xn, my last interval, and delta xn minus 1, the one before that, and so on, had a score, so maybe this is xn, had a score that was f of xn minus 1, or f of some representative point in that interval. So to find the average, what I would do from the first interval to the last interval is I would take the value of the function in that interval. I could call it f of some representative point ci, or I could just take the right endpoint as my representative and multiply that by the weight, or the amount of values that had approximately that height, and sum all those up. That would be the top of this fraction where I'm calculating the average. But then I would need to divide by the sum of the weights. So those weights are just delta xi. Now, in order to make this, you can see I'm sort of treating all of these values as though they have the same height, even though the function's actually varying in these short intervals. So what I should do to get a better value is to take the limit as the norm of the partition tends to 0. So I slice finer and finer, I'm really just slicing the top sum finer and finer and slicing the bottom sum finer and finer. So I have the limit as the norm of the partition tends to 0 of this sum, the sum from I equals 1 to n of f of xi delta xi, over the limit as the norm of the partition tends to 0 of the sum from I equals 1 to n of delta xi, and these two limits are definite integrals. So we get the integral from, on top we get the integral from a to b of f of x dx, and down below we get the integral from a to b of dx. Well, actually the integral from a to b of dx is pretty simple, because you have, it's like you're adding up the sums where from a to b the value of the function is always 1. So the area of that rectangle is easy. It's 1 times the base, because the height is 1, the base is b minus a, so we get 1 times b minus a. So we actually get this formula then. We have the integral from a to b of f of x dx That's each observation times its weight, and we're summing all those up. And then we're just dividing by the sum of all the weights. So dividing by b minus a, you can see that gives you exactly that formula for the average